This diagram of Earth's atmosphere shows a massive imbalance. 78% of the air we breathe is just one element, nitrogen gas. We are constantly walking through an invisible, nearly limitless ocean of it. But there is a serious biological problem with all that abundance. Vital crops like wheat and corn, the plants that keep humanity alive, cannot absorb a single molecule of this airborne nitrogen to fuel their growth. They are starving in the middle of a feast. The issue comes down to atomic architecture. The nitrogen molecules floating in the air consist of two atoms locked together by a stubbornly strong triple bond. It is one of the toughest chemical connections in nature, leaving the gas completely inert and inaccessible to plants. Human survival depended on forcing those nitrogen atoms apart. To sustain a growing food supply, we had to find a way to access that nitrogen and turn it into a form plants could actually use. Nature already had a hidden solution. Living silently inside the roots of certain plants are microscopic bacteria like Rhizobium and Azotobacter. These bacteria rely on a specialized enzyme called nitrogenase. It physically manipulates the nitrogen molecules, prying those triple bonds apart so the plant can assimilate the individual atoms. They achieve this with incredible elegance. The bacteria fix nitrogen perfectly at mild ambient temperatures and standard atmospheric pressure. But the bacterial process is slow and localized. In the early 1900s, global population growth began to outpace the land's natural fertility. We were depleting the world's limited deposits of natural fertilizers, and nature's quiet pace could no longer prevent a coming shortage. To avoid global starvation, humanity had to figure out how to forcefully replicate this delicate, microscopic bacterial magic on a monumental industrial scale. In 1909, German chemist Fritz Haber made a pivotal breakthrough. Working with fragile glassware, he successfully fixed atmospheric nitrogen purely by artificial chemical means. But Haber's tabletop setup produced only tiny drops. It fell to an engineer named Carl Bosch to take this delicate experiment and scale it up into a heavy metal industrial reality. This schematic outlines their foundational recipe. On one side, you draw atmospheric nitrogen. On the other, hydrogen from natural gas. Both flow into a central mixing chamber. To work, they must be blended in a strict proportion, exactly a 1:3 volume ratio. Gathering the ingredients in the right ratio was the easy part. The true challenge was figuring out how to force these stubborn elements to actually bond without the help of nature's gentle enzymes. Their substitute for biological enzymes was chemistry by brute force. First, they subjected the mixture to scorching heat. Inside thick reactors, the temperature is pushed to 450 degrees Celsius, causing gas particles to collide frantically. Simultaneously, they crush the heated gases under immense pressure, 200 times the normal pressure of Earth's atmosphere. Yet even with extreme heat and crushing pressure, the reaction is too slow. A chemical catalyst is required to truly stand in for the biological enzyme and drive the reaction forward. That crucial catalyst is iron. A fine dust of crushed iron powder is injected directly into the superheated, pressurized chamber. To boost the iron's efficiency, they mix in chemical promoters: aluminum oxide, potassium oxide, and molybdenum. Under this immense stress, the unbreakable nitrogen triple bonds finally shatter. The free atoms immediately grab onto hydrogen, snapping together into new, three-pronged molecules of ammonia. By substituting nature's quiet biology with extreme violence and heavy metals, Haber and Bosch successfully manufactured synthetic ammonia. Today, that chemical reaction takes place continuously inside towering industrial behemoths. Massive distillation towers and thick pipeworks contain the extreme physical forces at work. The liquid ammonia produced here is immediately transformed into the world's most vital synthetic fertilizers: urea, ammonium sulfate, and ammonium nitrate. Those chemicals result in millions of tons of packaged synthetic fertilizer, stockpiled and ready to be deployed across the globe. When farmers began injecting these artificial nutrients into exhausted soils worldwide, agricultural yields exploded. Food production successfully kept pace with a rapidly climbing global population. Today, the Haber-Bosch process is the unseen pillar of modern existence. By forcing an industrial replication of a microscopic natural phenomenon, humanity learned to pull the food that feeds billions, quite literally, out of thin air.